Welcome to this lecture. This is the fourth lecture of week 6. In this week, we are interested in looking at pointwise limits of distribution functions, and through which we have discussed a new mode of convergence, which is called weak convergence. So far, we have listed some equivalent conditions for weak convergence, and in the previous lecture, we have discussed some important properties of this weak convergence. In this lecture, we are now concerned about existence of limits for such sequences of distribution functions, and more precisely we are interested in the question when the limit function is a distribution function. To recall what we have observed earlier, in the setting of Helly's selection theorem, we have looked at limits, and in general what we have understood that the limit function need not be a distribution function. We have looked at certain explicit examples to establish this fact that in general we have no hope of getting a distribution function. In this lecture, we are going to discuss a explicit condition which will be equivalent or which will characterize this exact setting and will answer our question. So, let us continue discussing using the lecture notes. Alright. So, we are back to the setting of Helly's selection theorem, and here we are looking at a sequence of distribution functions on the real line. The Helly's selection theorem suggested that we can extract some subsequence and it will converge to a non decreasing right continuous function in the sense of pointwise limits, but with the additional caveat that the pointwise convergence will hold only at the continuity points of the limit function and not necessarily at all points on the real line. Now, if we consider the correspondence between the probability measures on the real line and distribution functions on the real line, this result we can state in terms of again probability measures on the real line. So, here in either case, whether we are looking at it from the perspective of distribution functions or from the perspective of probability measures, we are essentially unable to conclude that in general that the limit function that we obtain is a distribution function. So, this is a problem in general. If we state the same question in the case of probability measures, we are unable to conclude that the limit measure that we will obtain is a probability measure. In fact, if we go back to one of our earlier examples, in example 3, we considered the degenerate random variables at n. So, the nth random variable x n is degenerate at n, and what we observed that the limit of the distribution functions exist, but it actually turns out to give the identically 0 function. What we want to obtain is some additional condition which will help us avoid this escape of mass or escape of probability to infinity. Exactly what is happening is that the probability focus or the probability mass is moving to the right as n increases, and that is what we are calling as escape of mass or escape of probability to infinity. We want to stop this by introducing this following important concept, which we call as tightness for probability measures. We are going to say that a sequence of probability measures denoted by mu n is tight if given any epsilon there exists some compact subset of the real line denoted by k epsilon. So, it depends on the choice of epsilon such that all the probability measures assign at least 1 minus epsilon probability to this specific compact set. All right. So, what we are saying is that you fix any epsilon, you can find one compact set possibly dependent on the choice of epsilon such that all the probability measures assign at least probability 1 minus epsilon to these compact sets. So, this is some kind of a uniform bound that we are insisting on, and this is what we are going to call as the tightness for this sequence of probability measures. Now, we go back to this explicit example of degenerate random variables at n, and we observe that the condition for tightness actually going to fail. But before that, to understand this tightness, we state these condition that we stated in terms of certain compact sets in terms of other formulations. What we observe is that this earlier condition is equivalent to these two new statements. So, the first statement goes like this: fix any arbitrary epsilon, then you can find numbers a epsilon and b epsilon, two real numbers, with a epsilon strictly less than b epsilon. So, that you can consider intervals of this type such that all the probability measures uniformly assign at least 1 minus epsilon probability to this specific left open right closed interval. How do we see the equivalence with the earlier compact set business? So, here note that k epsilon, if it is a compact set, then it is closed as well as bounded. Therefore, it must be contained in some closed bounded interval a b. Now, what we do is that we look at the real line, we write down these points a and b. So, by considering any a epsilon smaller than a and we consider these left open right closed interval, we immediately observe that k epsilon is a subset of this interval left open a epsilon to b, and choose b or call it as b epsilon, and hence we have one immediate example of a left open right closed interval having probability at least 1 minus epsilon. Since the probabilities assigned to this k epsilon is at least 1 minus epsilon and this left open right closed interval is bigger than that. So, it will have at least that much probability. On the other hand, if we start with one specific such left open right closed interval, so we are now given this a epsilon to b epsilon, then if we want to go back to our earlier setting, all we have to do is to look at this compact set, which is this explicit closed and bounded interval. So, here again, as long as the left open right closed interval gets uniformly at least 1 minus epsilon probability, then since this closed bounded interval is bigger, it will also have at least 1 minus epsilon probability, but this closed and bounded interval is a compact set and that is going to give us one such choice of a compact set as required in the definition. So, therefore, the definition is equivalent to the first statement that we have stated, and this statement 1 will be useful in our later arguments that we discuss in this lecture. We are also going to consider condition in terms of the corresponding distribution functions. What we say is that given any epsilon positive, we must have again two such choices of real numbers a epsilon and b epsilon, a epsilon strictly less than b epsilon, such that the distribution functions evaluated at epsilon uniformly is less than epsilon and the distribution functions evaluated at b epsilon is uniformly at least 1 minus epsilon. So, again please take it as an exercise that this second statement is again equivalent to the earlier statements. So, we have restated the tightness in terms of certain left open right closed intervals and also in terms of the corresponding distribution functions. So, this is what the corresponding equivalent statements look like, and we are going to use these equivalent statements in our discussions involving tightness. So, let us look at one explicit situation where tightness does not hold. So, this was as pointed out earlier, discussed earlier in example 3, that we are considering a sequence of random variables, the nth random variable being degenerate at n. So, here what is happening, that the probability law is assigning the full mass or the singleton point small n, and therefore, if we fix any specific compact set, that will be contained in some large enough interval minus n to plus n, and therefore, for subsequent n's the focus will be shifting away from such intervals, and therefore, the corresponding compact sets will keep getting mass 0. So, therefore, the sequence of probability laws or this sequence of random variables that we are considering here will not have the corresponding property of tightness. So, that is going to be failing in this explicit example. Now, we are going to discuss a very important result that will tell us that tightness is very much important in the understanding of this kind of weakly convergent sequences of probability measures. So, the theorem goes like this. Theorem says that we start with some sequence of probability measures on the real line. Then the following two statements are equivalent. First statement says that look at a tight sequence of probability measures. This is equivalent to the following fact that given any further subsequence which is denoted by mu and k's, we can extract a further subsequence denoted by mu n k l such that there exists this limit in the sense of weak convergence. Meaning, if you have any subsequence mu n k, you can extract weakly convergent subsequence mu n k l, and the convergence will happen to a probability measure as required. All right. So, what we are saying is that tightness essentially implies that the limit that we obtain for subsequential limits at least will give us probability measures at the end. So, let us see the proof. So, we start in the forward direction. We assume that the given sequence of probability measures is tight. Now, let us start with any subsequence mu n k. We want to extract further subsequences. So, let us focus on corresponding distribution functions denoted by f n k's. Now, here we just go back to the Helly's selection theorem, which will allow us to extract further subsequence denoted by f n k l such that f n k l will converge in the pointwise sense to a non-decreasing right continuous function f, but only at the points where this limit function is continuous. So, this is the application of Helly's selection theorem. So, first we are starting with mu n k's, which is going to give us the f n k's, and from the f n k's we are extracting a further subsequence by the Helly's selection theorem. Now, let us focus on this specific further subsequence given by f n k l. So, here the limit that we obtained, which is this function f, a non-decreasing and right continuous function, which not necessarily is a distribution function in general, right. But let us look at the corresponding measure given by this function capital F, which is only known to be non-decreasing and right continuous. So, here the measure is uniquely determined by this property, that if you look at any left open right closed interval open A to closed B and assign the number f of b minus f of a to this, this extends uniquely to a measure on the real line, a Borel measure on the real line. So, this is by the Carathéodory extension theorem you can get such a measure. But now, let us focus on this specific measure through these subsequences. First of all, if we go back to the tightness that we have assumed for the original sequence, then what we get as a consequence is that for any fixed epsilon positive, we can choose two real numbers a less than b such that mu n of open A to closed B will assign the mass at least 1 minus epsilon to this specific interval, and this will happen for all n. However, if you look at the corresponding distribution functions corresponding to the mu n's, this is going to give us the fact that f n of b minus f n of a must again be at least 1 minus epsilon for all n. So, this is what we denote by the star relation. However, here the choices of A and B are coming from the definition of tightness, and here we a priori do not know whether limit function capital F is continuous at the point small a or small b. However, we can always choose a smaller a and bigger b such that they turn out to be continuity points of f, and then again for such choices of a as well as b, we can again get this uniform lower bounds given by 1 minus epsilon as given by star, because we have simply enlarged the interval to another left open right closed interval, but with the additional property that at the boundary points a and b the limit function capital F is continuous. And therefore, what we get if we focus purely on that specific subsequence through this relation star by looking at the corresponding pointwise convergences, we will claim that the limit function capital F has the property that f of b minus f of a must be at least 1 minus epsilon. However, by looking at the corresponding measure that we obtained through the cathode ray extension theorem, it says that the limit measure assigns the mass at least 1 minus epsilon to this interval open a to closed b. But since we are looking at any arbitrary epsilon and obtained this choice of an interval, then this implies that the limit measure that we have obtained is actually a probability measure, and hence by our construction what we have actually obtained is that these specific subsequential limits that we are considering is actually mu, that is the subsequence that we have constructed out of these probability measures converge to mu, and therefore, we have proved the forward direction that there is some probability measure appearing as a subsequential limit. So, we have started with tightness and proved this, but now we are going to see the opposite direction. So, to prove the opposite direction, we are assuming that Roman 2 holds, meaning we will get subsequential limit in the sense of weak convergence, but suppose that the original sequence is not tight. We are going to obtain a contradiction to this, and we will claim that we must have that the original sequence has to be tight. So, let us see. So, we start by looking at the definition of tightness. As long as this sequence is not tight, then there exists some epsilon for which the relevant condition is not true, and therefore, for some epsilon given any such a less than b, we must have that mu n of open a to closed b, this must be less than 1 minus epsilon. So, the exact opposite inequality is given as per the definition. But now, let us look at this setting that for positive integers k, I will choose to look at these specific choices of a and b, where a is minus k and b is plus k. Then what we can do is that for this epsilon positive that we are working with, we are going to get essentially certain numbers n k, meaning for some n this condition is going to fail, and that is what we denote by n k. So, for each fixed small k, we are choosing a and b, which is giving us this left open right closed interval, and when this condition is going to fail, that is going to give us some choice n k. So, that is what we write down here. Now, let us come back to our assumption. So, here we are assuming the existence of subsequential limits. So, what we are saying is that any subsequence will have a further weakly convergent subsequence. Let us denote it by mu n k l. Now, suppose the limit is denoted by mu. Here what we do is that let us look at the distribution function f of this limit. So, here we have to look at the corresponding continuity points, and let us choose certain continuity points c and d. So, here what we know is that f of d minus f of c must be giving us the exact measure associated to this left open right closed interval c d. What we can choose are c and d, c small enough and d large enough such that this measure is at least 1 minus epsilon over 2. Now, for large enough number L, this interval open C to close D will be contained in minus k L to plus k L. The mu n k L, the mass that it assigns to this interval left open right closed interval will be less or equal to this quantity, but according to our earlier argument this must be less than 1 minus epsilon. So, we have two inequalities involving the measures associated to this left open right closed interval C D. On one hand, we have this double star relation where the measure in terms of the limit probability measure is said to be at least 1 minus epsilon by 2. On the other hand, we are saying the individual terms that approximate the same value must be less than 1 minus epsilon. So, this gives you a contradiction, and therefore, we conclude that our original assumption that the original sequence is not tight, that must be false. Therefore, we must have the original sequence being tight, and therefore, it gives us the second part of our statement, and this completes the proof. What we have now established is that we have a sequence converging in the sense of either a sequence of probability measures or a sequence of distribution functions to ensure that the limit or a subsequential limit turns out to be a probability measure in the case of sequences of probability measures, or a distribution functions in the case of a sequence of distribution functions. We need tightness, and this is actually an equivalent condition. So, we are now going to focus on interesting comments involving tightness. So, we are going to focus on also applications of tightness. So, first we look at a modified version of these equivalents that we have observed, and then we are going to apply it to obtain other interesting results. Let us see. What we do now here is that we first look at a sequence of tight probability measures. Then, if we look at the fact that the subsequential limits are unique, then the conclusion will be that the original sequence must converge to that unique limit. So, let us restate it again. Suppose there exists one single probability measure such that any weakly convergent subsequence that you consider converges to that same probability measure, then the original sequence must converge. So, just to compare this type of a convergence in the sense of real number sequence, we also have a similar result that states that if given a sequence of real numbers, if it so happens that every subsequence has a further subsequence converging to a fixed real number. So, that fixed real number does not depend on the choice of the subsequences. Essentially, we are talking about uniqueness of the subsequential limit, then the original sequence must converge. So, we are stating a similar result, but for a sequence of probability measures converging in the sense of weak convergence. Let us see the proof. So, we are seeing that we start with the assumption that we fail to have the original sequence converging. So, we will like to obtain some contradiction to this fact, and again we will say that therefore, the original sequence must converge. So, we will start with the assumption that the original sequence does not converge, obtain a contradiction and then say therefore, our original assumption was false and the original sequence must converge. Let us see. So, if the original sequence does not converge weakly, then for some continuity point small x of the corresponding limit distribution function of the probability measure mu, we must have the corresponding sequence of distribution functions which is given by mu n of this interval does not converge to this value which is again given by mu of this same interval. So, there must be some such continuity point of the distribution function capital F which corresponds to this measure mu. So, we are going to focus on that specific continuity point small x and observe certain interesting contradictory facts. So, let us start by looking at the fact that this real sequence f n of x does not converge to f of x. Then by the definition of a limit, for some epsilon positive, we will have some subsequence of the original sequence such that the distance from this value must be at least epsilon, right. So, it will have infinitely many choices of n k's for which the terms in the subsequences are further away by this epsilon distance from this number f of x. So, therefore, we should not have the convergence. So, this is just by the definition, but let us now write down the same fact in terms of the mu n k's. So, the f n k's are exactly given by mu n k's as assigning values to these type of intervals. So, therefore, this difference must be at least epsilon and this must happen through that subsequence essentially for all such k's. In particular, we observe that if we consider any further subsequence mu n k l that cannot converge weakly to mu, because it is further away and on such intervals we are not having the corresponding convergence of the corresponding distribution functions, even though the function capital F is continuous at the point small x. So, therefore, we will fail to have the fact that further subsequences are converging weakly to mu. However, by our hypothesis and some application of our earlier theorem that we must essentially have such subsequential limits, this is ending up with a contradiction, that on one hand we are claiming that we will have a further subsequence converging weakly to mu, on the other hand we are having the fact that it cannot converge and we cannot have such subsequences. Therefore, this contradiction is arising from our original assumption and therefore, our original assumption must be false and we must have the original sequence of probability measures converging to mu, and this completes the proof. And this understanding about tightness is going to give us our next important result, and this is called Levy's continuity theorem. So, just to go back to our setting of the discussion of equivalent statements that we had discussed earlier, the convergences for probability measures on the real line in the sense of weak convergence, we have talked about equivalent characterizations through the corresponding characteristic functions. That was the pointwise convergences for the characteristic functions. That is exactly the Levy's continuity theorem. However, to prove this, we are going to make use of certain equivalent facts that was also listed earlier as part of Heilevre theorems or the application of the Portmanteau theorem that we had mentioned earlier. But we are going to use those other equivalent conditions in terms of the corresponding expectations of bounded and continuous functions and use those equivalent conditions to prove that weak convergence of probability measures is equivalent to pointwise convergence of corresponding characteristic functions. We will come back and prove the assumption in terms of the integrations of bounded and continuous functions later on. So, let us see the proof of Levy's continuity theorem. Alright. So, just to clarify, here in theorem 3 we are trying to prove the equivalence between 1 and 14. This is the connection between convergence of probability measures in the sense of weak convergence and pointwise convergence of corresponding characteristic functions. And we are going to assume that this equivalence already is true, as already discussed earlier in theorem 2. We had not proved theorem 2 as of yet, but we are going to prove it later on. We assume this for now and prove our statement involving convergences through characteristic functions. Let us see Levy's continuity theorem. The statement says that we look at a sequence of probability measures converging in the sense of weak convergence to mu. Now, suppose the corresponding characteristic functions are denoted by this. The statement says that this weak convergence is equivalent to the pointwise convergence of the corresponding characteristic functions. This is the Levy's continuity theorem. So, let us see the proof. So, in the first part we assume that the sequence of probability measures converge weakly to mu, and we would like to establish the corresponding pointwise convergence for the characteristic functions. So, here we want to establish it for any arbitrary u. So, fix such an u. Look at the continuous functions on the real line given by small x mapping to cos of u x and small x mapping to sin of u x. These continuous functions in fact are also bounded, and therefore, if we appeal to integrations involving bounded and continuous functions, we observe that the limit of the characteristic functions evaluated at u can be expressed in terms of these two separate integrals through these integrations involving bounded and continuous functions, and therefore, if we assume that fact, then the limit must be in terms of the corresponding integrations of the same bounded and continuous functions, but with respect to the limit measure mu. But this is exactly the characteristic function of mu evaluated at the point u. Therefore, we have obtained the corresponding pointwise convergence very easily by assuming that weak convergence for the sequence of probability measures holds, and the fact that corresponding integrations for bounded and continuous functions also must be true. All right. So, this gives you one side of the equivalence. On the other side, we assume that the sequence of characteristic functions converge pointwise. So, to start off the proof, we first show that the original sequence that we are working with must be tight. So, let us see this fact first. So, to do this, we establish certain important estimates. Let us take any u positive and look at these kind of integrations. We observe that these integrations that we are looking at are real valued by observing certain interesting facts. So, let us look at 1 minus the characteristic function of mu n evaluated at t and integrate it from minus u to plus u divided by u. Explicitly write down the formula of the characteristic function. So, this will give us a inner integration here in terms of the probability measures. Here we have two integrations. If required, we will split in cos of t x plus I times sin of t x and expand. Then we can justify the exchange of integrations here. Here we will simply go back and apply the Frobenius theorem, and once this exchange of the order of integration is allowed, then first we will have the dt integration with in the terms of Lebesgue measure first, then with respect to the underlying probability measure. But then here you note that again exponential I t x that can be split in terms of its real part as well as its imaginary part, and what we can observe is that one part by looking at the property that it is an odd function is not going to contribute, and therefore, this earlier expression simplifies to this expression. A similar calculation was done earlier when we obtained the inversion formula for characteristic functions. Please go back and check this. But now note that this last expression that we are looking at, it purely involves real valued functions and the integration with respect to certain probability measures. So, therefore, these quantities that we have obtained at the end must be real valued. So, therefore, the original integration that we have started off with must also be real valued. But now, we focus on certain properties of the limit characteristic function and obtain certain further estimates. Here, we first look at the fact that the type of functions that we have obtained here, the sine function is bounded between +1 and -1, and therefore, if we restrict our integration from the real line to the specific intervals of type mod x greater or equals to 2 over u. So, this is a smaller interval than the real line. Therefore, here the earlier estimates can still remain. Therefore, we will have this lower bound given by these expressions. So, here we have used two facts. One, the sine functions that we have used here is less or equals to 1. So, that is the first thing, and the second fact is that the intervals given by minus infinity to minus 2 by u and union with 2 by u to infinity, which is exactly the interval described by mod x greater than 2 by u greater or equals to 2 by u, that gives us a lower bound. So, here we are using these two facts, that these are getting estimated through properties of measured theoretic integration. Now, let us focus on the fact that on this specific type of range of integrations that we are now considering, here what is happening is that the function or the value small x takes very specific values away from 2 over u in the sense of the modulus, and therefore, if you plug that in the estimates, then this quantity, the integrand 1 minus 1 by u x, that can be observed to be at least 1 by 2, and multiplying by the 2 that appears on the right hand side, we will end up having this further lower bound, because the integrand now is 1, and therefore, we are just looking at the measure of such sets, which is the union of these two intervals that we have discussed. So, therefore, what we observe is that we have this further lower bound given by mu n's assigning this mass to this specific type of union of intervals. But now, let us focus on the corresponding limit characteristic function. Here the characteristic function always is continuous at 0. So, therefore, 1 minus the characteristic function is also a continuous function, but let us look at its value at 0. So, now since any characteristic function takes the value 1 at 0, so 1 minus the characteristic function takes the value 0 at 0. Then using the continuity and using properties of integration, given any epsilon positive, we can find u positive such that this quantity will be close to that value 1 minus phi mu at 0 by a very small amount. So, it will be close by this distance, all right. So, here we have used the fact that the function 1 minus phi mu, the characteristic function of mu, that is continuous at 0, and we are using properties of integration here and using that relevant continuity, all right. But then we also are assuming the pointwise convergence of the corresponding characteristic functions, and therefore, we can appeal to integrations of this type on such finite intervals minus u2 plus u. Here we observe that since the characteristic functions are also uniformly bounded, then we can appeal to bounded convergence theorem. Then for this above epsilon that we have fixed earlier, these integrations in terms of the characteristic functions of mu n's must be less or equal to these quantities simply by the convergence by some epsilon over 2 distance. So, that is just by the limiting property as applied from the bounded convergence theorem, but this must hold for large enough n. But again for large enough n we have this upper bound, but the right hand side the integration is in terms of the characteristic function of the limit measure mu, which we are trying to establish, and here we have the upper bound given by epsilon by 2. So, taken together we end up with a upper bound given by epsilon. So, therefore, we have a uniform bound for large enough n for these type of integrations. So, going back to our earlier estimate, what we conclude that for any epsilon positive, we are going to have a choice of u positive such that for large n, mu n assigns this kind of mass to this kind of sets, which is always less than epsilon. Now, this happens for large n's, and therefore, if you also consider the first few mu n's, then taken everything together we can establish that all the total sequence that we are considering is tight. So, this part is left as an exercise to you, please check this. So, for a stage n onwards we have the relevant bound that we need. However, you just have to include the first few finitely many mu n's which we did not consider here. Taken everything together, it can be shown that the original sequence is tight. So, this is left as an exercise for you, please check this. So, as soon as we have established the tightness of the original sequence, then consider any weakly convergent subsequence of the original sequence. Now, suppose this weakly convergent subsequence converges to some probability measure nu on the real line, but then if we appeal to the first part of our theorem, then we immediately have that it will converge in the sense of pointwise convergence of the characteristic functions to this as well as that, meaning the limit that we are considering as mu, that characteristic function, the corresponding characteristic function matches with the new probability measures characteristic function. But since characteristic functions uniquely identify the corresponding probability measures, so this was discussed earlier in week 5 theorem 9, then we must have mu equals to nu. Therefore, what we have concluded is that if we consider any weakly convergent subsequence of the original sequence, then this must converge to this fixed measure mu, which is a probability measure, and therefore, we appeal to our earlier result in proposition 5 that uniqueness of subsequential limits will imply that the original sequence must converge in the sense of weak convergence. So, therefore, we have proved this result. So, we have now proved that convergence of probability measures in the sense of weak convergence is equivalent to pointwise convergence of characteristic function. This result will have very nice applications, which we are going to see in the next lecture. We stop here. Thank you.